Welcome to the course on biostatistics and design of experiments. We will talk about two more distributions. One is called the exponential distribution, the other one is called the hypergeometric distribution. All these are very useful in biology as well. Yesterday we talked about the beta distribution, if you remember. Okay, beta distribution, let me recollect again. The probability density function f for x is given by this particular formula. We have the gamma function of alpha plus beta, gamma function of alpha, gamma function of beta, x minus a divided by b minus a raised to the power alpha minus 1, b minus x divided by b minus a raised to the power beta minus 1. So, here we have 4 parameters a, b. So, your x will lie between a and b, and alpha beta are 2 parameters which are always greater than 0. So, we can always have a as 0 and b as 1. So, x may be lying between 0 and 1. So, that gives you a simplified version of the beta probability density function. Okay, of course, Excel also has a beta dist function, as you can see, beta dist x, alpha, beta, a, b. These are the 4 parameters. So, it calculates and lets you know what is the probability density function. What do I say? Beta distribution is very important. We can get different types of shapes of graphs using different values of alpha and beta. So, that is the main advantage, especially if you are a modeling and simulation person, and if you want to generate different types of graphs, then this particular function is very useful. As you can see, we can get exponentially rising, linearly rising, similarly linearly dropping, exponentially dropping, and then curves which gives you a maximum and minima. So, all these we see in biology also. So, if one is interested in modeling in biological systems, modeling biotransformations, modeling bioreactors, then beta distribution is very useful. All I have to do is manipulate these alpha and beta values, and you will end up getting different types of functions. Okay. Now, let us look at some more distributions. The one is called the exponential distribution. Actually, exponential distribution, okay, it is related to Poisson distribution. Okay. If you recollect, Poisson distribution gives you events, okay, like there are 3 road accidents in the city in a period of 1 month. There are 10 infant mortality in the South India over a period of 6 months. So, that sort of informations it gives, events, number of events. But the exponential distribution gives you the time between events. Okay, what is the time it will take for the next event to happen, that sort of times it gives. And another important thing is it has a key property of memoryless. That means the previous information and the new information are not correlated at all. Actually, just because a previous information has happened or an event has happened, that does not mean the succeeding event will be dependent on the previous event. Okay. So, for example, road accidents, there is no correlation that because a road accident did not happen yesterday or happened yesterday, there will not be another road accident tomorrow, so there is no correlation on the events. So, it is used to describe the time or distance until some events happen, like as I said, how long it will take for the next road accident to happen in the metro city of India, that sort of information it can give. So, it is useful, and as you can see, it is related to Poisson distribution. So, the probability density function comes up with a relation like this. You have lambda e power minus lambda x. If you remember, in Poisson distribution we had only one term lambda, right. So, exactly this also has only one term lambda here, and then x is the probability density function for x. X is greater than 0 or equal to 0, okay, and generally the graphs look like this, they will be falling down for different values of lambda. So, the mean for this function is 1 by lambda, okay, and the variance is given by 1 by lambda square. So, the random variable x that equals distance between successive events of a Poisson process with the mean lambda greater than 1 is an exponential random variable, okay, and this is the probability density function. Okay. For different values of x, as you can see, the graph gives you the probability density function. Okay, so you can calculate the cumulative distribution also. All you need to do is it is given by this particular relation 1 minus e minus lambda x, okay, for values of different values of x, and it, because it is cumulative, it keeps building up as shown in this figure, whereas the probability density function, the probability density function keeps falling as a function of x. Okay. So, cumulative distribution function is nothing but a integral of 0 to x naught for x less than or equal to x naught. So, 1 minus e power x naught by mu. Okay. So, I can integrate it and do the substitutions, and you can end up having this type of relationship. Okay. That gives you the cumulative distribution function. Okay, so, what is the relation between exponential and Poisson? As I mentioned, Poisson is a discrete random variable that measures the number of occurrences of some event, whereas exponential distribution gives you the length of the interval between occurrences, okay, how long it will take for a particular event to take place, whereas Poisson distribution tells you how many events. Okay, that is why they are both interrelated. So, exponential distribution is a continuous distribution and it has no memory term attached to it. That means just because an event has happened, that does not mean that will have a bearing on the next event, like the road accidents, there are no bearing on that at all. Okay. So, for an exponential random variable x, we have p x less than t1 plus t2 x greater than t1 is given by p x less than t2. That means there is no whether you take a time on January 1st or whether we take time on February 1st, the time for the next event to happen will be independent, whether I start my starting point as January 1st or I start my starting point as February 1st. So, that is the lack of memory which is characteristic of this exponential distribution. So, we will look at some examples. Before that, let me also talk about the Excel. There is an Excel exponent dist which is given by x comma lambda comma cumulative. Lambda is the parameter value, x is the value of the function. Cumulative, if it is true, it gives you a summation. Cumulative, if I give it as false, then it will return the probability density function at that particular point actually. Okay. So, let us look at one simple problem. So, it is an epidemic is happening. So, when there is an epidemic, you will have patients coming regularly to clinics. So, that could be modeled using an exponential distribution function. Their time of arrival could be modeled using an exponential distribution function. So, a medical center, what it does is it estimated that on an average there are 10 patients visiting the center between 10 a.m. and 12 p.m. Okay. In that 2 hours 10 patients come in. Okay. However, it has been more than 30 minutes since the last patient visited. What is the probability for that? So, for 30 minutes nobody came. So, what is the probability of that? So, average time for each patient's arrival is 2 hours because 10 a.m. to 12. So, 2 into 60 because we are converting into minutes divided by 10. So, that gives you 12 minutes. So, average time for each patient to arrive is 12 minutes, that is lambda. Now, we want to look at time interval between patient's visit follows an exponential distribution with a mean of 12 minutes, right. So, we can get 1 minus e power minus lambda x, okay. Lambda is nothing but 12 minutes, okay. And so, we are converting that into hours, okay. Then take 0.5, so that gives you 0.095, okay. So, actually this should read as 60, 12 by 60 because we are converting that into hours, multiplying by 0.5, 0.5 is your x, 30 minutes. So, this is equal to 0.095, okay. So, we can do the same thing here using the Excel function, okay. So, Excel function is exponent dist, Excel function exponent dist x lambda comma cumulative, either it could be true or it could be false. So, let us look at that Excel function. So, we go to the Excel function, we say we will say exponent dist comma 0.5, that is 30 minutes, okay, 12 by 60, because we are converting the 12 minutes into 60. So, the cumulative, okay, so we could call it true or false here. We will look at both cases, okay, 0.095. So, the probability for 30 minutes, okay, probability for 30 minutes nobody came to the clinic because of the illness is 0.095. We put cumulative here because when we say for 30 minutes nobody came, it could have been 1 minute, 2 minutes, 3 minutes, 4 minutes and so on actually, okay. So, that is why we put it as true, okay. So, the same thing is obtained from this equation also, 1 minus e raised to the power minus 12 by 60, where the 12 is converted into hours, that is why we are dividing by 60 multiplied by 0.5. So, that gives you 0.095. So, we get the same answer using the Excel command also, okay. So, it is simple. Now, it lacks memory. So, that is most important property of exponential distribution. Okay, let us look at another problem. X denotes the time between the detection of a particle with the Geiger counter, and then we can assume that x is an exponential distribution with lambda is equal to 1.5 minutes. The probability that we detect a particle within 30 seconds of starting the counter, okay. So, the probability 30 seconds within that time is given by 0.3, okay. So, that is the time it takes for that to come back, it takes about 0.3, okay. So, we can use the Excel function also to get the same answer. So, we can put in exponent dist into x into lambda into cumulative to get the same answer also, and so the probability is 0.3. Now, suppose we turn on the Geiger counter and wait for 3 minutes without detecting a particle, okay. In this situation we detect a particle within 30 seconds of starting the counter. So, that gives you 0.3, okay. So, we can put in the same thing here using the Excel command also, sorry. It is given as 30 seconds. So, we need to convert that into minute, that will be 0.5, okay. Then next one is 1.4 minutes comma, then we say true, okay. So, we get exponent dist, okay, 1. Okay, so we get it as 0.69. So, when we do it as 1 minus this, that will come to 0.30, okay. So, this is how you do it. So, it is a probability of 0.3 that we that we detected a particle within 30 seconds or within 0.5 minutes. Now, we turn on the Geiger counter and wait for 3 minutes, okay, without detecting a particle. What is the probability that a particle is detected in the next 30 seconds, okay. So, you see we wait for 3 minutes and then we want to look at whether particles come within that 30 seconds, or we start our Geiger counter and within 30 seconds we detect a particle, okay. So, just because we have not seen a particle for 3 minutes, do you think the probability will increase? No. According, if we start doing these calculations, we will see we will end up again with the same answer, okay. We will end up again with the same answer, which means even after waiting for 3 minutes without detecting a particle, the probability of a detection in the next 30 seconds is the same as the probability of detection in the 30 seconds immediately after starting the counter. So, whether I wait for 3 minutes and then look for a particle within 30 seconds, or I start my Geiger counter and look for a particle within 30 seconds, you will get the same probability. Okay. Why? Because as I said, exponential distribution is memoryless. So, it does not consider that because it has not seen a particle for a very long time, that the probability will increase. Okay. So, that is the beauty of this particular distribution. Do you understand this problem? So, initially we start the Geiger counter and within 30 seconds we see a particle. So, we will say the probability is say 0.3. Then we start the Geiger counter, but we wait for 3 minutes without detecting a particle, and then what is the probability that we will detect a particle within that 30 seconds, that is 3 minutes, and between that 3 minutes and 3 minutes 30 seconds you will come get the probability as the same, and there will not be any difference at all because of the characteristic of this exponential distribution. Okay. It is not that the probability will increase because we have not seen a particle for a long time. Okay. So, the probability of will not change because unlike other distribution, because we have not seen a event occurring, the probability will not change at all in the exponential distribution. Okay. So, let us look at another example. The average mammalian genome mutation rate is 2.2 into 10 power minus 9 per base pair per year. Okay. Okay, this is taken from this reference. So, this rate is given. What is the probability that the interval between successive mutations at a particular base pair is 80 years or less? We assume that as the human lifespan. Assuming a genome of 3 billion base pairs and independent mutation events, how many bases are expected to be mutated over this time span? Okay, so, we assume it as independent mutation and we will assume it as base pair, okay, billion pairs. So, this is the average mutation and we are given 80 years. Okay. So, we want to look at what is the probability that the interval between successive mutations or is about 80 years or less. So, what do we do? 1 minus e power lambda x, okay. X is your 80 years, lambda is 2.2 into 10 power 9, sorry 2.2 into 10 power minus 9. So, when we multiply by 80 we will end up getting 1.76 10 power minus 7. Okay. So, the probability that a mutation will take place in 80 years or less is given by this particular probability. Okay. So, we can use the same thing using our Excel function also. Okay. So, we have the Excel function, it has got expand dist x is equal to 80 years, okay, into 2.2 into 10 power raised to the power minus 9 into true, you get 1.76 10 power minus 7, you understand. So, that is the probability of a mutation taking place in 80 years or less. Okay. Now, if you assume 3 into 10 power 9 as bases, okay, then we would expect that after 80 years there will be 528 bases that should have got mutated. Do you understand how to do this? We multiply 3 into 10 power 9, okay. So, we multiply 3 into 10 power 9 with 3 into 10 raised to the power 9 multiplied by this particular term, that will give you 528. So, totally 528 bases would have been mutated. Okay. So, of course, here we assume that the possibility of a site getting mutated twice. So, we every time we assume that double mutation is extremely low. So, it is only single mutation. So, by assuming that, we are able to get a probability of 1.76 into 10 power minus 7, and we assume there are about 3 into 10 power 9 bases, there would have been 528 bases that would have got mutated in the 80 years. So, you understand. So, this is an exponential distribution, it tells you the time between events. So, it calculates the probability of the time for a particular time to for an event to happen. It has got no memory, just because we look at some event in the month of January, or we look at some event in the month of February. Okay. The starting point does not matter, the probability of that particular event occurring, the time for the probability is going to be the same. Okay. So, if you are looking at, say, accidents on the roads, so whether we look at it from January, how long it will take for that accident to take place, or when we look at February, how long it will take, it will be the same. Okay. So, that is the special characteristic of this exponential distribution, and it is related to Poisson distribution in the sense that Poisson distribution tells you the number of events, whereas the exponential distribution tells you the time between two events. So, this is also a very important distribution to know, especially in the area of biology, as you can see, is quite useful. Okay, now let us look at another distribution, okay, that is called the hypergeometric distribution. Okay, what is hypergeometric distribution? So, generally here in a hypergeometric, the sample size is relatively large when compared to the population of a discrete distribution, okay, that is called hypergeometry. So, the sample size is quite large, whereas normally in normal distribution we sample may be small, population is very large. We take 10 students from a university and measure their heights. Okay, so, the population is huge, whereas in a hypergeometric distribution the sample size is sort of considerable to the population size. Okay, so, it is not really very small. That means the population is not very large. So, the sample and population are not very far away, then that sort of distribution is called the hypergeometric distribution. Okay. Okay, so, it gives you a discrete random variable, the set of all possible values, at most a finite or a countable infinite number of possible values. So, it gives you discrete distributions are constructed from discrete random variables actually. Okay. So, it gives you a set of all possible values, that means a finite or a countable infinite number. Normally infinite number is not countable, but here in this particular distribution we call it infinite, but it is still countable. Okay. So, it is given by this relationship, the probability okay, C S x C n minus S n minus x divided by C n and small n, okay, where your n is your sample size, okay, S is the event supposed to have happened, okay, n capital N is your population size, small n is your sample size, okay, x is the number of successes in n trials. When I take a sample size of small n, then my x is the number of successes, whereas in the population of capital N, capital S gives you the possible number of successes. Okay. Do you understand? For example, if I have 100 balls in a box, out of that 10 balls are black, the capital S, if I am picking up balls, I want to pick up black balls, capital S will be 10 and N could be 100. Okay. And when I take a sample of say 5, the small n will be 5, and if I get one black ball in that, the success x will be 1. So, this calculates the probability. So, you understand that the capital N, the population, although we call it population, has got a finite size, unlike the normal distribution where population is very large. Okay, here the mean mu is given by S n by capital N. S is the possible number of successes, n small n is the number of trials, capital N is the population. So, n by n is some sort of a ratio. So, S that gives you the mean, okay, very logical to think about. Variance and standard deviations are given like this. The variance is S, that is capital S multiplied by n minus capital S multiplied by small n multiplied by n minus n divided by n square n minus 1. This is how the variance is given by. Okay. So, this is the mean, this is the variance. So, the hypergeometric distribution is based on the concept that the sample size is not very small when compared to the population size, or the population size is finite, it is not infinite unlike the other type of distribution. Okay. So, this is also very useful distribution, we will come across in many situations and many problems even in biology and non-biological studies as well. We will look at each one of them more in detail. Okay. So, this is the SCX is nothing but S factorial divided by x factorial divided by s minus x factorial. Okay. So, this is the symbol for that. So, s factorial in the numerator, denominator will have x factorial and s minus x factorial. So, if you look at this will have n minus s factorial in the numerator, small n minus x factorial in the denominator, then capital N minus s minus small n plus x factorial again in the denominator. That is how it is broken, and this will show capital N in the numerator, denominator will have small n factorial and also n minus n factorial also in the denominator, and that is how the terms look like in hypergeometric distribution. Okay. So, we can also look at problems in hypergeometric distribution, and as I said it is very useful type of analysis to carry out, especially in biological systems also, and this distribution is quite useful in that sense, where you have a limited number of population and a sample you take from that limited number of population. Okay. Thank you very much. We will continue in the next class.